Hello and welcome back. So I thought it might be fun for our next series to come a little closer to home and talk about our beautiful, wonderful solar system. So we're going to start with all the planets and then move on to some of the other bodies. So first up is Mercury. Mercury is named after the Roman messenger god because it moves very quickly around the sun, just like the messenger god was said to move quickly in delivering his messages. It's also known in Greek as Hermes. Mercury is actually the smallest of the planets. It's only a little over 5% as massive as Earth. That means that its surface gravity is a little bit less than 2/5 of the Earth's. And so if you weighed 100 pounds on Earth, you would weigh only 38 pounds on Mercury, although your mass would remain the same. Mercury is not only the smallest planet, but it's also the closest planet to the sun. It orbits at a distance of only 0.39 AU, which gives it a year, or one revolution around the sun, that takes about 88 Earth days. One really cool thing about being so close to the sun is that the sun's gravitational field is so strong there that Mercury's orbit actually is affected by general relativity, and so it's non-Keplerian. The way that this manifests is that its perihelion, or its closest point of approach to the sun, actually changes over time, and it changes faster than we would expect just based on Keplerian motion. Now, before Einstein was able to use general relativity to predict this anomalous precession of Mercury's orbit, it was hypothesized back in the 19th century that there was actually another planet interior to Mercury that was causing these changes in its orbits. Now, this was considered pretty plausible because a similar technique had just been used to discover Neptune. So this hypothetical planet was called Vulcan, and astronomers were searching for it until they realized, in fact, that this was not a signal from another planet, and it was, in fact, a confirmation of general relativity, one of the well-known confirmations of general relativity. Another side effect of being so close to the sun is that Mercury experiences a very strong tidal force from the sun. So we're used to thinking about tides in terms of here on Earth, of the ocean levels changing over time. And this is caused by the moon's gravity on the Earth, creating a tidal bulge in the oceans, which rotates around and causes tides. However, tidal forces are found in many places. And so basically you get a tidal force anytime there's a strong differential in gravity between one side of a body and another. So when you're considering an extended body and not just a point source, the gravity on each side is going to be slightly different because gravity depends on your distance from the other object. So Mercury, being so close to the sun, has actually a stronger gravitational pull on the side that's closest to the sun and a less gravitational pull on the side that's farthest away from the sun, which creates a tidal bulge in the planet. Basically, it's a departure from being a perfect sphere. It makes it a little bit bulgy at the equators. And now, because of that tidal bulge, that interacts with the gravity of the sun, and it prefers to be aligned in a certain way. And this has actually led to what we call a spin-orbit coupling of Mercury. So you can see spin-orbit coupling in some other ways. For example, a kind of famous one is the moon and the Earth, right? The moon is on a 1-to-1 spin-orbit coupling, which means to say that it rotates once every time it revolves once. And this is why the same side of the moon is always facing the Earth, and why we have a dark side of the moon, which is called the dark side because we don't see it, not because it doesn't receive sunlight. When you have a spin-orbit coupling, it relates the length of a day to the length of a year on a given object. And on Mercury, it's not a 1-to-1 spin coupling, but it's actually a 3-to-2 spin coupling. So this means that every 3 Mercury days is 2 Mercury years. It's a pretty interesting phenomenon, and it actually confused astronomers for a while. They expected it to be in a 1-to-1 spin-orbit coupling, and it was only much later, when they were able to take more detailed measurements, that they actually measured the spin more accurately and realized it was in this 3-to-2 spin-orbit coupling. So like I said, Mercury is the smallest planet. It's only a few times the mass of the moon, in fact. And actually, if you look at Mercury, it does tend to bear a superficial resemblance to the moon as well. It's too small to hold on to an atmosphere, both because of its very small size and also its proximity to the sun, which makes it more difficult. It has a very plain, rocky surface that is not, like Mars, it's not red or something. It just kind of generally looks grayish. And it has a lot of craters on the surface, indicating, it's had this bombardment, and like the moon, it doesn't have an atmosphere to smooth out these craters, and so you are tending to get quite a lot of them. Although actually, Mercury is slightly less cratered than the moon for various reasons, but it does kind of look like it. But one way in which Mercury is very different from not only the moon and the Earth, but really all of the other planets we know, is that it has an incredibly high iron or metal content. So basically, in a terrestrial planet, you tend to get differentiation. So you have a core and a mantle of like different, they tend to be made of different elements. And the heavier elements tend to sink to the core, as you might expect. So the core is going to be very metal rich, and then the mantle is going to be less metal rich. So one way that we can look at Mercury and look at its metal content is also to look at its core mass fraction. So basically how much of its mass is in its core. Now for the Earth, this is about 30%. About 30% of the Earth's mass is located within its core. For Mercury, it's actually 70%. So this is a very large core mass fraction, and it has a very, very high iron content relative to silicates and rocks. So it's a very metallic, dense planet. And actually, the exact cause of this disparity with the other planets isn't really precisely known. The leading theory is the giant impact theory, where that Mercury was basically hit with a very strong collision that stripped off a lot of its silicate and mantle material, and so left behind kind of this predominantly core material. And that's also part of the reason why it would be so small, because it lost all of this mantle material. So this model works pretty well, but there's actually some debate about whether or not all of that material that was stripped from the planet would actually just fall back onto the planet, and so you wouldn't actually get a very metal-rich planet in the end. And there are some other theories that I'm not going to go into all the details on, but this is actually something that scientists are still researching to figure out why Mercury is so dang dense. So the existence of Mercury has been known for basically ever. The very first recorded knowledge of Mercury was back in the 14th century BC, marked on tablets made by an Assyrian astronomer. Now in the 17th century, so several centuries later, 33, however many centuries later, the telescope came along, and people of course wanted to turn it onto all of the planets. And so Galileo did observe Mercury through his telescope. However, he wasn't able to achieve enough resolution to see phases in Mercury. So like the Moon and Venus both have phases where they're only partially lit by the sun, because they are between us and the sun. So for example, on the outer planets that are farther out than us, we don't see phases really, but with the inner planets we do. However, Mercury was so small and so far away that with these first telescopes they couldn't actually resolve that. Kepler calculated the orbit for Mercury, and he predicted when it would transit, and then that first transit was observed in 1631 by Pierre Gassendi, and I think this was the first planetary transit of a star ever seen, so back in the 17th century. And then in 1639, they were finally able to get powerful enough telescopes to actually see the phases of Mercury. So this was first observed by Giovanni Zuppi. And then as telescope power continued to increase and we were able to observe better and more detailed observations, in the 19th century they started making maps of the surface of Mercury from what they could see from here on Earth. And that ability to observe was increased in the 20th century when Soviets in 1962 made the first radar observations of Mercury. So they were able to bounce radar waves off of Mercury. And then American astronomers in 1965 were able to use similar technology using the very recently departed Arecibo radio telescope, actually that's located in Puerto Rico, to detect and measure the spin of Mercury. So in 1965, this was when they first really measured the day length, basically, of Mercury and discovered that 3-to-2 spin coupling that I mentioned earlier. Now we tend to hear a lot about Mars and a little bit about Venus when it comes to space exploration, but maybe we don't hear so much about Mercury, where there's actually only ever been 2 space probes to Mercury. And the reason for this is that Mercury is actually very difficult to get to. It requires a lot of delta V. Now, delta V is short for delta velocity or change in velocity, but it's not exactly a simple change in velocity. It's more a measure of basically how difficult it is or how much energy it's going to require to put something into various places in the solar system based on the change in velocity. I'm not going to get into the details, but a lot of delta V, the more fuel you need, basically. And because Mercury is so close to the sun and moving so fast, it requires a lot of delta V. It actually requires more delta V to visit Mercury than it does to escape the solar system entirely. But NASA has done it twice. So the first time was in the 1970s with Mariner 10. This was a flyby mission, so it made 3 close passes to Mercury. The closest it passed was about 200 miles from the surface. And this was their first chance to get really detailed images of the surface of Mercury. Unfortunately, because the same portion of the surface was lit by the sun for the entire mission, we weren't able to map the whole thing. We only got about 45% of the surface of Mercury mapped during the Mariner 10 mission. And one thing that came out of the Mariner 10 probe that was really exciting was that they discovered Mercury has a magnetic field, which was a total surprise to scientists because they thought Mercury was too small to have a dynamo, which is basically the thing that they think powers and creates magnetic fields in terrestrial planets. So the detection of a magnetic field around Mercury was really surprising and really exciting because it meant there was more to learn about how planets get magnetic fields. And then after its planned flybys, the Mariner 10 probe ran out of fuel, so it was shut down, and it's still out there in its own orbit around the sun, probably, just humming along. So then many years later, in 2004, NASA launched the Messenger mission. So like I said, Mariner 10 could only map a portion of the surface, so Messenger was able to map the entire thing. Messenger did 3 close flybys, and then it actually entered into Mercurian orbit in 2011. So basically the goal of the Messenger mission was, one, to complete the mapping of the surface and also to measure things about the magnetic field that was so exciting, this discovery from Mariner 10, as well as to use its orbit to gain more information about the kind of mass distribution of Mercury and its interior structure. And it also had instruments to help measure elemental abundances on the surface of Mercury. And then in April 2015, the mission was completed and the Messenger probe was crashed into the surface of Mercury when it was done. But good news for all you Mercury fans, because ESA and JSA, so the European Space Agency and the Japanese Space Agency, have launched a mission called Bepi Colombo that is also going to Mercury. This mission was launched in 2018 and it should reach Mercury in 2025. Like I said, Mercury is difficult to get to. So that's going to be really exciting, and I'm sure there's going to be a lot of really cool images and discoveries and scientific information that comes out of that. So that's Mercury, our smallest, closest planet to the sun that is in its spin orbit coupling at 3:2 and under the influence of general relativity. Pretty cool planet. Very small, very fast. The messenger among the planets. So I hope you enjoyed this video about Mercury. Next time we'll be talking about Venus, and so I hope you come back. All right, thanks for watching. Bye.